Hey everybody, Dr. A here, and in this video we are going to be exploring another example of torsional shear stress. So if you didn't see the first example, you should check out that video. I also have a background video on torsional shear stress that kind of goes over the basic assumptions and the governing equations. So let's go ahead and get started with this example. So in the given information, we're being told to compute and draw the torsional shear stress distribution in the wall thickness of the hollow shaft at point B, okay? So go ahead, write this down, maybe pause the video, and you want to draw these figures out. Remember, you want to write stuff down. Watching is usually not good enough. Write it down, take good notes. So in this figure, we have this kind of three-dimensional looking figure. We have a fixed connection back here at point A, and then we have a free connection, a free end right here. So this is like a cantilever shaft. And point B is some distance along the length of the shaft. Even though we're not explicitly told what these lengths are, we know that point B is just somewhere on the, within the length of the shaft. Now you can tell this is a hollow shaft because if you look very closely here, you see the hole in the shaft. And if you also notice this shaft, it's not explicitly being sustaining an applied torque moment. It's actually sustaining 2 point loads that are generating a torque moment, okay? So if we look at the shaft cross section over here on the right, we see this annulus or a ring shape where we have this hollow center here. And so the thickness, the wall thickness is represented here, and that's 0.5 inches. And then the outer diameter is given to us as 4 inches. And so on one edge of the shaft, we have a downward pointing 10-pound load. And then on the exact opposite end of the shaft, edge of the shaft, we have an upward pointing 10-pound load, okay? So that's what we're looking at. Maybe pause the video, write and draw all this out on your paper, and really visualize what's going on here. So let's write solution now, and let's go ahead and get this going. So we know that the governing equation for torsional shear stress is tau equals T rho over J, where rho is a radial distance measured from the center of the shaft outwards, okay? T is the internal torque moment, and J is the polar moment of inertia of the cross section. So let's go ahead and figure out which one of these terms we can easily get. Well, first we can say the torque moment is going to be equal to what? Well, it's not explicitly given, but you have these couple forces on either edge of the shaft. And so if you remember from statics, couple forces are two forces of equal magnitude pointing in opposite directions, and they will cause a tendency of rotation on whatever they're acting on. So this torque moment is going to be equal to 10 pounds times the perpendicular distance in between the couple forces, which in this case is the full outer diameter of 4 inches. So this is going to give us 40 pound inches as our torque moment. Now that's going to be right here at the edge, at the end of the shaft right here. So we can maybe resketch this, and we can show that. Let's try to resketch this nice and neat. Okay, so we can see that we have the outer diameter of 4 inches, and then this is generating this torque moment like this of 40 pound inches. Now, you could do method of sections at the point of interest, point B, and discover that the torque at point B is just that 40 pound inches, okay? Now, I can just look at that and I can tell that just by looking, because there are no other applied forces or torque moments anywhere on the shaft. This is not like the previous example where we had 2 torque moments applied along the length of the shaft. Here, you just have this couple forces at the end causing a tendency of rotation at the end of the shaft, and there's nothing else along here. So by observation, we can say that the torque moment at B is just equal to that 40 pound inches, okay? So that's still what we're looking. We're still looking at this kind of diagram at point B. So that gives us capital T, we can kind of check that off. Let's go ahead and calculate the polar moment of inertia, J. Now remember, this is for the entire cross section, and we have an annulus. We have a ring here, right? It's a hollow section. So for a hollow circular section, the polar moment of inertia formula is going to be pi times the outer diameter to the fourth minus the inner diameter to the fourth, all over 32. Now, we know that the outer diameter is 4 inches. Now, we can easily calculate the inner diameter as the outer diameter minus 2 times the wall thickness. Now, you may be wondering, why is it minus 2 times the thickness? Where does this minus 2 come from? Well, remember, the outer diameter is 4 inches from here to here, and to get to the inner diameter, you need to subtract off the thickness on either side of the shaft. So outer diameter is from edge to edge of the shaft section, and then you're subtracting one thickness and then a second thickness to give you this inside diameter here, okay? So when you have 4 inches minus 2 times the thickness, that's going to give you 3 inches here, and we can go ahead and calculate the polar moment of inertia. I'm going to use my TI-36X Pro calculator. I love this calculator. So we're going to say 4 raised to the 4th power minus 3.5. I'm sorry, not 3.5. Minus 3 to the 4th power times pi over 32. And I get 17.18 inches to the 4th power. Okay, so that's my polar moment of inertia for this section. Now we'll go ahead and check that off. Now we need to know about rho. Well, if you read the directions very carefully, what do the directions say? Compute and draw the torsional shear stress distribution in the wall thickness of the shaft, okay? So what we really need is a couple of values here. So I'm going to draw this much bigger, okay? I'm going to draw this hollow circular shaft much bigger. Let's see if I can draw an inner circle better. There we go. And we've got that 40 pound-inches here, causing a rotation here. And so what we're looking for is we are looking for this shear stress distribution that is coming from that applied torque moment. So we're looking for something like this. Okay, now remember, the shear stress distribution is linear increasing from the center of the shaft, okay? So it starts at 0 and then it linearly increases. Now, you may be wondering, where's my little vector arrows for the middle portion of the shaft? Well, remember, this is hollow. There's nothing here. If there's nothing in this middle part, then it cannot sustain any stress. So what we're looking for is the stress distribution in the solid part, in the thickness of the shaft, okay? Now, it's not going to start at 0 at the edge of the shaft. It's going to start at 0 at the middle of the shaft, okay? So what we need is two values. We're going to need a tau interior, tau sub I, and a tau exterior, tau outer, tau O, okay? And so how do we calculate these? Well, we're going to say tau inner is going to be equal to T times the inside radius over J, where the inside radius is equal to rho at the inside surface of the shaft, okay? And so we're going to say tau inner is going to be 40 pound-inches times, now what's the inner radius? Be very careful here. What is this inner radius? The inner radius is going to be 1.5 inches, right? Because the inner diameter is 3 inches. So the inner radius is 1.5 inches. So be very careful. Don't be mixing up your radius and your diameter. And then we're going to divide that by 17.18 inches to the fourth. And so we're going to calculate this as 40 times 1.5 divided by 17.18. And we get 3.49 psi, okay? And then we're going to say tau outer is T times the outer radius over J. And again, we're going to say where RO equals rho at the outside surface of the shaft. So tau outer is going to be 40 pound-inches times, what's the outer radius? Well, that's just 2 inches because the outer diameter was 4 inches. And we still divide it by the 17.18 inches to the fourth. So the polar moment of inertia is what it is. It's that value for the entire cross section. So that's not going to change. So we're going to say 40 times 2 divided by 17.18, and we get 4.66 psi. So if we sketch this out, we have the value at the inside surface, that shear stress is the 3.49 psi, and then the value at the outer surface, tau outer, is that 4.66 psi. So this is our sketch of the shear stress distribution throughout the thickness of this hollow circular shaft. So, so these are your two values, and you would have that figure accompany your values. So that's going to conclude this video. Thanks for watching. Please hit like and subscribe.